Hey guys, sorry that I cannot be in class today. I forgot that I had this meeting, so I wanted to just do a quick little recording here for you to walk you through the group work problems. So I have the first one up here. This one is a rental car agency has 15 cars in its lot. The following table shows the mileage of each car. Use the data to complete A through D. Okay, so calculate the mean of the population. You know how to do this already. We just highlight it. We can just look right down here. It'll give us the average. Or if we want to, we can use the average function and calculate the mean. That's simple. So round to one decimal place, 123.8. Then it asks us to do sampling error. So if you remember from the chapter, the sampling error is the mean of the sample minus the mean of the population. So this is our population mean. I'll label it that. And then it says calculate the sampling error using the first 5 cars in your row. So again, all we do is take the mean of the sample. 1, 2, 3, 4, 5. And then remember that the sampling error is bar x, or the mean of the sample, minus the mean of the population. So our sampling error is 1464.4. Next we have calculate the sampling error using the first 10 cars. So I'm just going to change this to first 10 and change this to the first 10. Now I can see that our sampling error is negative 934.7. And then how does increasing the sample size affect the sampling error? So what we saw here is it made it smaller, or closer to 0 in this case. So in general, increasing sample size makes the sampling error smaller. All right, so on to question 2. This one's a little bit tougher. So I'm going to go ahead and I'm just going to delete all this stuff and just show you how to do this one, which, like I said, I think is a little bit tougher. All right, so the first step of this is we have to find the standard error of the mean. And if you remember, that's in the book, the formula for it. And the formula is on page 306, standard error of the mean. The standard error of the mean is the population standard deviation divided by the sample size. So we'll just say pop standard deviation and sample size. All right, so this tells us right here it has a standard deviation of 12 and a sample size of 36. I'm sorry, it's the population standard deviation divided by the square root of sample size. So our standard error of the mean is going to be population standard deviation divided by the square root of the sample size. So, well, that's handy. Our standard error of the mean is 2. Okay, so the second thing we need to do is find the mean of our sample means. And we have no way of finding that, but if you recall, because of the central limit theorem, the mean of our sample means, as long as we have a sample size of 30 or greater, is going to be equal or roughly equal to the population mean. So we're going to use that number 42 as our mean of our sample means. All right, so here's where I think it gets complicated. So now it says to find an interval that includes 95% of the sample means, which means we're trying to find some point at which a bell curve is going to contain 95% of all values within it, which really means, if you think about it, that 2.5% off of the upper limit and 2.5% off of the lower limit would leave 95% of all available probabilities in the middle. I know that's a little bit confusing. So we have to find the point at which this is true. And so what we're looking for is what z-value is, what z-score is going to give us 97.5% of all the values. And the reason for that is because if we find the z-score, that leaves 2.5% of the values above that z-score and 97.5% of the values below that z-score. And remember, if we're trying to find an interval that contains 95% of all values, then we need to first find the upper limit, which would have all points 2.5% of the values above it, and then we'll have to find the lower limit, which will have 2.5% of all values below it. So I know that sounds a little confusing, so let's just look at how we would use Excel to do that. Sorry, I had a little bit of an interruption there. So the function we're going to use in Excel is norm.s.inv. So this gives us a standardized normal distribution, but it's giving us the inverse, meaning if we put in the probability, like I said, 97.5% or 0.975, it will return a z-score that will cover that. So it's telling us right here that 1.96 is the z-score at which 97.5% of all possible values will fall to the left of that z-score. So that's the upper end of our limit is 1.96, a z of 1.96. And then to find the lower limit in z, we have to use norm.s.inv, and we're going to put 2.5%. You'll see that that's negative 1.96, which is what we would guess. Okay, so the reason I use 2.5% again is because if we're going to find a curve, a bell curve that has 95% of all values in it, then it's going to have 2.5% of all values above that curve and 2.5% of all values below that curve. All right, so we know the z-score. So now what we have to do is use the formula. This is formula 7.4 on page 307 in your book for finding the z-score of a sample mean. But because we know the z-score we need, and because we know the mean of the sample means and the standard error of the mean, we're going to be solving instead for the sample mean at the upper limit and the sample mean at the lower limit. So you may have to check that formula out. So that formula is that the z-score equals the sample mean minus the mean of the sample means divided by the standard error of the mean. And we have all this information now, right? We have the z, the standard error of the mean, and the sample mean of the sample means. So it's pretty hard for me to show this on Excel. In essence, we're just solving for this. So if I solve for a z of 1.95, well, let me just do the math. I'm going to have to do the math. Let's see if I can figure out how to do that here. So if z equals bar x minus the mean of the sample means divided by the standard error of the mean, then bar x is going to equal z times, so let's put it upper limit. And again, this is on page 307. This is going to equal our z times our standard error of the mean plus our mean of the sample means. Our lower limit is going to equal the lower limit z, times the standard error of the mean plus the mean of the sample means. So this is the interval that will contain 95% of all values. I know that was confusing. I hope it is helpful to you. All right, for the third question, one college class had a total of 80 students. The average score for the class on the last exam was 85 with a standard deviation of 4. A random sample of 35 students was selected. Calculate the standard error of the mean. All right. So first, let me get rid of this old stuff. Remember that our standard error of the mean is a function of our population standard deviation and our sample size. So here, if we say, let's see, the class had 80 students, so that's our population. The average score was 85.1 with a standard deviation of 4.4. And then we have a sample of 35 students. There's our standard error of the mean. Uh-oh. Oh, look, I missed this one because I forgot. You remember we talked about the correction if we had a finite population, meaning if our population was small and our sample was at least 5% of the population. Here our sample is, almost half. We're talking 40%. So I've got to do this finite population correction factor. I know it's a crazy sounding word. But the finite population correction factor is just what it sounds like. It's to correct for the fact that that the finite population is going to skew things and make it a little bit too close to the mean. So the formula for this is on page 313 in the book, but it equals the square root of big N, which is the number in the population, so 80, minus little n, which is the number in the population. I'm sorry, in the sample, divided by big N, which again is 80 in this case, minus 1. So that's the finite population correction factor. I know that's a crazy sounding term. All right, so then in order to find the standard error of the mean, we take the calculated standard error of the mean, which we did right here, and we multiply it by the finite population correction factor. And that's going to give us, okay, now I've got a problem. Hold on just a second, guys, and don't judge me. Oh, I think I found it. I put 2 decimals in there. Heh. All right. Next, the probability that the sample mean will be less than 87 is, all right, so here's how we go about doing that. So we use the z-score formula, which again was on page 307, formula 7.4, to calculate what the z-score will be. So if we have a sample mean less than 87, what we have to do is we say, so our z-score equals our sample mean minus the mean of the sample means divided by the standard error of the mean. Okay. So to calculate our z-score, we're going to say this equals our bar x, which in this case is 87, minus the mean of the sample means. So again, remember, if we have at least 35 in the sample, then our mean of the sample means is going to be the same as the population mean. Okay. And then that's going to be divided by the standard error of the mean, which we have right here. That's going to give us a z-score. See, that's a pretty big z-score. And then, so to find the probability, all we have to do is use the function we already know, which is norm.s.dist. That's the standard normal distribution, where we use the z-score and then true for cumulative. And that's going to find the probability that of things falling to the left of 87. In this case, that's huge, right? So 0.9996, almost for sure. All right, now find the probability that the sample mean is more than 86. So again, we can go back to our z-score. We'll replace 87 with 86. That gives us the z-score for 86. Here's our probability for 86, or less, right? And then so here we're going to have to do this 1 minus that probability. And that'll give us the probability that it's more than 86, which is 0.0544. Finally, the probability that the sample mean will be between 84.5 and 86.5. So again, we take the upper limit, 86.5. There's our probability that it is to the left of the upper limit. I'm going to copy that, paste it here as a value. Then I'm going to do the same for my lower limit, 84.5. There's my z-score. There's my probability that it falls to the left of 84.5. And I'm going to say the probability that it falls between them is the probability of the upper limit minus the probability of the lower limit, or 0.8511. All right, and we're on to our last question. So here we have, according to a national study, 34% of taxpayers use computer software to do their taxes for a certain year. A sample of 125 taxpayers was selected. Complete parts A through D below. So this one's a little different because now, instead of knowing the numbers of people, we know proportions of people. So the first thing we have to do is calculate the standard error of the proportion. The formula for this is on page 318 in the book. And so the standard error of the proportion is equal to the square root of P, meaning the proportion, which in this case is 0.34, times 1 minus P, 1 minus, let's see, divided by N. In this case, N is 125. Oops, I didn't do an equal sign, and so Excel doesn't know what I'm talking about. All right, so again, it is P times 1 minus P divided by N. That's our standard error of the proportion. Got to watch your rounding. Second is, what's the probability that less than 32% of the taxpayers from the sample use computer software to do their taxes? So now we find the z-score of the sample proportion. Again, that's a formula on page 318 in the book. So to find the z-score, that is bar P, or the sample proportion, minus P, which is the population proportion, divided by the standard error of the proportion. Okay, so so this is going to equal the sample proportion, and that's this number they gave us, 32.32, minus the population proportion, which is 0.34, divided by the standard error of the proportion, which we just calculated. So there's the z-score that less than 32% of taxpayers use computer software. And then to find the probability of that, I use norm .s.dist, plug in the z, say true, and this will return the probability that less than 32%, which is 0.3185. The probability between 28 and 39% of taxpayers used it. So again, I'll use my upper limit, 0.39. Oops, too many decimals. So there's my probability for 0.39. Whoops, running out of space here. Let me just shrink this column down. All right. So I'm going to say that this equals, or I'm just going to copy this probability. This is the probability of my upper limit. And then I'm going to figure out the z-score for my lower limit of 0.28. Which gives me a probability of 0.07. And so the probability that it falls between those intervals is the probability of the upper limit minus the probability of the lower limit, or 0.8026. And then the question is, what impact would changing the sample size to 225 taxpayers have on the results? I think the easiest way to answer this is to simply come up here to where we're doing standard error and just change it to 225 and see what happens. So we can see our z-score went up from what it was. Our standard, let's see, our standard error of the proportion went down. It was 0.424. Now it's 0.03 or 0.04 to 0.03. And so our standard error would be reduced. We can narrow it down to those two, which would in turn reduce the probabilities or increase the probabilities. So here our probability was 0.8026. Now we see it's 0.85. So the standard error is reduced, which increased the probability. You could also go through the logic of how it all works too, but I just test it. All right, so that's it. Again, I'm sorry I can't be with you. I hope 22 minutes isn't too long, and I hope you have a great day.